In Islamabad and Lahore in Pakistan, and also in Kyoto, Japan. Today, he will talk about elementary properties of Bessel-Rees potentials. Please join me in welcoming Dr. Eridani. There's a microphone.
Okay, thank you. This is the source of my talk. These dissertations of my students from Lambung Mangkurat. As far as I know about the boundedness of these operators is only in here and the papers who wrote by us with Idris and Professor Hendra Gunawan. Now we try to prove the boundedness of these operators in homogeneous spaces. I mean these generalizations of Euclidean spaces with the metric and measure spaces on that spaces. First, for any nice functions, we consider the potential Bessel-Rees potential as follows. With the kernels have a form as a multiplications of Rees potentials, Rees kernels, and below is Bessel kernel. If gamma equal to 1, then E alpha 0 is a famous Rees potentials. We know from since 1938, Hardy, Littlewood, and Sobolev already proved the boundedness of this potential, these Rees potentials, from Lebesgue spaces to another Lebesgue spaces. Now, even in 1980, we already know the boundedness of these integral operators is sharps. It means that the constants on the boundedness is on the boundedness inequality is the smallest possible. Now we try to reprove the boundedness of Rees potentials using the properties of Bessel-Rees potentials. First, we try to prove that our kernels belong to some Lebesgue spaces. With the exponent of Lebesgue spaces is belong to the intervals that depend on n, gamma, and alpha. Even we try to make a equivalent norm of our kernel with some series, some convergent series, just like these theorems. Using a Young inequality about the boundedness of convolutions, we have the following equations about the boundedness of Bessel-Rees potential that depend on the norm of its kernels. We know that these conditions is already the same as a general Young inequality in measure spaces. We proved this theorem in 2018, and now we try to generalize, to extend this inequality in more bigger spaces than Lebesgue spaces. Now we choose classical Morey spaces as extensions of Lebesgue spaces. Now we define the Morey spaces as follows. Remember when the norm with the exponent p equal to q, then we have Lebesgue spaces, the previous spaces. And also, if we have a condition on p and q, then we also have L to the power of infinity. I mean the function that its essential supremum is finite. Now, using Holder inequality, we also have this. We know that our Morey spaces, our new spaces, contain the Lebesgue spaces. We know as p equal to q, then we come to the classical Lebesgue spaces, as the following inequality shows. Now, we have a nostalgia about the risk potentials. We know in 1938, Hardy, Littlewood, and recently Sobolev already know the inequality, and we have the inequality is a Hardy-Littlewood Sobolev inequality. In 1980, we also know the smallest C0. We also the smallest positive C0 found by Elliott Lip. That's why this inequality is optimal. Now in 2000, it's about 2002, with my teachers, I try to make P near to Q. I try to make P near to Q. Now we have results that if P equal now we have a result. If P near to Q, then we have the following inequality, but now with the risk potentials is a continuous mapping from LP to Morey spaces LPQ. Even we can consider this inequality as a different from this, just because the power of norm of E alpha 0 is P also. But surprisingly, the condition for the following inequality is the same as the previous results in 1938. Now we come to the next step. In 1969, we try to prove the risk potentials is bounded operators on classical Morey spaces. Just like this inequality shows, we must extend the boundedness of these operators on Morey spaces. First, Spanner already have this inequality, but he has not published these results. We only know these results in the papers by Chuck Petrie in 1969, and Chuck Petrie told us that these results is come from Spanner. Is P1 equal to Q1 and P2 equal to Q2. we will have a Hardy-Littlewood-Sobolev inequality as well. Now we can consider SPAN's results as an extension of Hardy-Littlewood-Sobolev results. The next one is about 1987, Adams, Sciarenza, and Frasca. Actually, Adam already have these results in 1972. Now, Sciarenza and Frasca reprove the Adams results by the different methods, and they have these results that we can consider these results is stronger than the SPAN results. It means that SPAN results can reprove by using this inequality as a corollary. SPAN results is a corollary of these results. Now we come to prove the boundedness of Bessel-Riesz operators. First, we must consider the kernel of these operators, and we must find some function spaces bigger than Lebesgue spaces, such that the kernel belong to that spaces. Now the candidate is classical Moré spaces, I think. We know that K alpha gamma belong to some classical Moré spaces if one of the following condition is fulfilled. So if a condition is fulfilled, then K alpha gamma belong to this classical Moré spaces. The same result also true if we consider the second conditions. From the previous results, then we have the following. Of course, this is only if we have, we know that if we only use a Young inequality, then the norm of the kernel only belong to the Lebesgue spaces. Now we try to reprove the Young inequality previously, but now we must prove that the kernel belong to the classical Moré spaces. Now we have the method as Elias Stein told us, that our operators is divided by the two parts, the good part and the bad part, or the small part and the big part. Usually E alpha gamma is an integral that the first is integral inside the balls, and the second is the integral outside the ball. The radius of the ball, of the arbitrary ball, is R. And then the first integral is dominated by the maximal functions, and the second integral is dominated by the norm of function f. Now we know that this inequality is true for every r, for every positive r. Now we try to minimize this expression below, such that so it means that if we minimize this expression, we must choose the sum r. Now we try to minimize. Usually, if a plus b is minimum, so it means a is equal b. That's why if this term is equal, so we can choose r. R is equal to maximal functions divided by the norm of f. That's why we consider this f is non-trivial. It means that f is not zero functions. Now, after we choose R appropriately, then we get the Hedberg inequality. We know Hedberg inequality is already famous since 1972, if I'm correct. It's 1972. We already know this, but we we use it again and again in harmonic analysis, in everywhere, in every problem, almost in every problem about the boundedness of fractional integral, and now we use it to prove the boundedness of Bessel-Riesz operators. Now, after we multiply this with the power of q and we integrate, then we have the following inequality, that is there exists C5, positive C5, such that Riesz potentials is bounded from LP to LQ. Now this inequality, we can consider this inequality as a refinement of HLS inequality. We know that this inequality, Hardy-Littlewood-Sobolev inequality C0 is already found, the smallest one, the optimal one. Now we know that C0 is have a form like this. C0 is equal C5 multiplied by the kernel of Riesz the Riesz kernel. Now now we know that the C0 explicitly is contain the Riesz kernel, the norm of Riesz kernel. Now we can consider this as a refinement. With the same method, the previous results, as in the previous result, with the same method, we also have the following. But now we can consider Riesz potential is continuous operators from Lebesgue spaces to another Morey spaces. But now the constants that we can write it contain the norm of Riesz kernels. Now, as usual, surprisingly, the above theorem is have a corollary. We can consider the results, the next results, as a substitute for the weak type inequality. We know if Riesz potential, we know that Riesz potentials is continuous from L to the power of P to L to the power of Q with P is greater than 1. If P equal to 1, then we have the weak type inequality. We know it from Hardy, Littlewood, and Sobolev also. But now, if LQ is, we substitute LQ by the classical Morey spaces, we can remove the weak type inequality with this strong type inequality. It means that if F belongs to the Lebesgue spaces, then we still have this strong inequality, but LQ is, now we substitute LQ with another classical Morey spaces. Actually, some people think that, is it true that classical Morey spaces is almost the same with weak type Lebesgue spaces? I think this is still an open problem, since some people also investigate the behavior of these operators on weak type Morey spaces. I don't know. Okay, the next one. Now we try to the next steps. We prove the Bessel-Riesz operators and Morey, that is bounded on Morey spaces. We try to reprove Adams-Yarensa-Fraska results, and from the boundedness of Bessel-Riesz operators. Now we have these results, and surprisingly, if we choose gamma equal to 0, we already have the Adams-Yarensa-Fraskas, but now with the constants is contain the norm of kernel Ries. Now we have the more explicit form of the constants in Adam Siarenza Frascas. And after this joint research with Professor Hendra Gunawan and Idris, I try to doing something in homogeneous measure metric spaces. Now we consider the operators, but now in measure metric spaces. But now we know that k, x, y is functions of two variables, and I don't know how to define the norm, the Lebesgue norm for two variable functions. I try, but I don't know. I still doubt about it. I try to define the Lebesgue norm for a function of two variables with the following definitions. Even I doubt about this definition, I still have the same results. Okay, how many times left? 15, okay, thank you. With these definitions, I will have this, I reprove that K is still belong to the Lebesgue spaces with the measure mu, and the measure mu is equivalent with the R to the power of beta. And finally, I have our first results as follows. We can consider this inequality as the boundedness of Bessel-Ries operators in weighted sense. I mean, we have the different weight, eta and mu. We can consider this as the weighted case for the inequality. Now, for the next one, I try to define the general Morey spaces like this. And after this, I have some results. But now, the boundedness of Bessel-Ries operators is still consists of the kernel that is belong to the LP, to the Lebesgue spaces. And after this, we still have another results, but this we can also consider this as a generalization of Adam, Siarenza, and Frasca. Now, what if I try to define K as that belong to the Morey spaces? I don't know how to define the norm for the functions of two variables, but I still doubt about this definition, so the research is stopping here. I still have a lot of homework to doing something about this, since I still doubt about these definitions. Thank you very much.
Mic test, mic. Mic. Okay, thank you very much for the interesting talk, Dr. Eridani. I will now open the floor for questions from the audience. We will sit down. Questions from the audience? Yes, first one. Sir, please.
Yeah, thank you. I'm just curious about
Can you state your name first and then? Thank you.
My name is Nanang. I'm from Universitas Gajah Mada. I'm just curious about the constants in all the inequalities. So
Which one? Which?
all the inequalities.
Okay.
So if I remember correctly, then you said that you got an optimal bound, right? Or optimal constant.
Yeah.
Okay. My first question is that what do you mean with the optimal constant? And the second question is every constancy independent with the choice of f, or if you have a function f, then you will have corresponding constancy. Yeah, thank you.
Yes. So the first question is for the bound C.
Okay. The first one is only one result is optimal, C0. The next result is not yet found. What is the smallest constant? Okay. Only we know C0 have the smallest constants. It means that C0 is not depend on F. It's only depend on P, Q, and N. Of course, P, Q is also depend on alpha and N, but not depend on F. The smallest ones make the inequality is equality. It's found in 1980. It's about 1980 by Elliot Lip. Okay, I think it's also answer the second one. Yes? No. The optimal constant is only C0. Up to now, the other is not yet found. Even in 1969, we know nothing about the smallest one. We know nothing. Even in the classical one, we know nothing about the smallest one.
How difficult to find the constants? I think that because C is every constant is independent with the choice of
Yes.
the function, right?
Yes.
So how difficult to find the constancy?
Yeah. Okay. But in we know f is range from every function since Lebesgue spaces. So we must find that we know C0 we know about the norm operators. Okay, we know about the norm operators. The norm operators of E alpha 0 is less than or equal C0. So, can we find f such that the norm of operator E alpha 0 equal to C0? So, Elliot Lip found one function such that norm operator E alpha 0 equal to C0. Now, the problem is the function that found by Elliot Lip can also work with this inequality. I don't know. I have no idea how to. I think Elliot Lip is lucky. He found something. He found a function that makes C0 multiplied by the norm of f is equal to the norm of E alpha 0.
Okay, thank you for the question. I think the second question has already been answered. It's independent. So I call Professor Ida.
Thank you for the opportunity. I have two things. The first one, I just want to ask whether you already work on the weak type and the sufficient condition for your result. And then the second one, probably on your last slide, you put eta For the last slide. For the definition of Morris species. Yeah. I think I'm working on a similar one, but on hypergroup. If we put the lambda, if we put the definition almost like this one, then I will restrict the lambda between 0 and 1, and the necessary condition is a little bit different with the known result. But if I put the lambda, the power is lambda over n, then the necessary condition exactly the same as the known result. That's all. Thank you.
Okay. The first one is about the characterizations. Am I right? Okay. About the characterizations is already done. Mr. Idris and Professor Hendra is already know about the characterizations. But for the homogeneous measure metric spaces, I have no idea how to prove a characterizations. I think this is a new one, the new topics. But for the second one, I know nothing about the working in function spaces with group. I'm sorry, I have no comment about the...
No, I just give a comment. Probably,
Yeah, okay.
Probably you could put the power is not lambda, but you put lambda over n. If you put lambda over n, probably the necessary condition for your work will similar to the known result. No need a lot of new condition.
We can make a joint research.
Yes.
Thank you very much.
Okay, thank you for the questions. Are there more questions from the audience? Professor, what do we mean when we prove something about the boundedness of the operators? Okay. What does this imply? I mean, does it imply continuity or?
The main problem of these topics is a papers in Proceeding of American Mathematical Society in 1999 by Kazuhiro Kurata, Nishigaki, and Satoko Sugano. They try to apply the boundedness of these operators, risk potential and Bessel risk potential, to determine the elementary properties of Schrödinger equations. But Professor Hendra knows that the boundedness of these operators, for example, this, in those papers, the C1 is bigger. Now we try to make C1 is smaller. I mean, if C1 is getting smaller and smaller now, the elementary properties of the Schrödinger equation is about to be optimal, but I don't know the meaning of this optimal. Maybe you can read the papers.
Okay.
I don't know.
Okay. Thank you very much. If there are no more questions from the audience, please join me again in thanking Professor Eridani. Thank you very much.